The discovery of Comet 3I/Atlas has rapidly become one of the most scientifically significant astronomical events of the decade, not simply because a new comet was found, but because this object is fundamentally different from the countless icy visitors that regularly pass through the inner solar system. Detected by the Atlas survey on July 1, 2025, the comet immediately drew attention due to the unmistakable shape of its trajectory. Unlike ordinary comets that follow elongated elliptical paths bound to the sun's gravity, 3I/Atlas is traveling on a hyperbolic orbit. This mathematical distinction carries profound implications. The comet is not native to our solar system. It is an interstellar object, a true wanderer between stars, passing briefly through our planetary neighborhood before continuing its journey back into the depths of interstellar space. As only the third confirmed interstellar object ever observed, and the first clearly active comet among them, 3I/Atlas represents a rare and fleeting opportunity to study material that formed around another star entirely. From the moment its non-native origin was confirmed, scientists recognized 3I/Atlas as a kind of cosmic time capsule. Unlike asteroids and comets that formed within the same protoplanetary disk as the Sun and planets, this object condensed in a distant stellar nursery under physical and chemical conditions that may differ significantly from those that shaped our own system. For planetary scientists, this makes 3I/Atlas an invaluable comparative sample. Its ices, dust, and gases preserve information about the temperature, radiation environment, and chemical inventory of another planetary disk, offering a natural experiment that no spacecraft mission could realistically replicate. Every photon captured from this comet adds to a growing dataset that allows researchers to test whether the processes that built planets around the Sun are universal or merely local variations in a much broader cosmic pattern. As 3I/Atlas moved closer to the Sun, telescopes around the world and in space began to document dramatic changes in its appearance. Among the most visually striking developments was the emergence of a greenish glow surrounding the comet's coma, revealed in high-resolution images taken by the Gemini North Telescope. This green coloration is not merely aesthetic. It is a well-known spectral signature of diatomic carbon, a volatile molecule commonly abbreviated as C2. When sunlight excites these molecules, they fluoresce, emitting light at characteristic wavelengths that produce a vivid green hue. What made this observation particularly compelling was the fact that earlier images of the comet showed a redder, more subdued coloration. The shift in color signaled a fundamental change in the chemistry of the gases being released from the nucleus. This evolving color palette tells a detailed story about the comet's internal structure and thermal response. As 3I/Atlas approached perihelion, its closest pass to the Sun on October 29th to 30th, 2025, increasing solar radiation penetrated deeper into the nucleus. Early activity was likely driven by highly volatile surface ices that sublimate at relatively low temperatures. As these were exhausted or blown away, heat reached layers containing more complex and heat-sensitive compounds. The sudden prominence of diatomic carbon indicates that these deeper reservoirs were being exposed and activated. For scientists, this provides quantifiable evidence that the comet's outgassing profile is not static, but evolves rapidly as a function of solar heating, revealing stratified layers that may have remained untouched since the object's formation billions of years ago. Perhaps the most groundbreaking development in the study of 3I/Atlas came not from visible light at all, but from the detection of X-rays. Until now, no interstellar object had ever been observed emitting X-rays, making this a historic first. On December 3, 2025, the European Space Agency's Newton Observatory successfully captured X-ray emissions from the comet when it was approximately 282 to 285 million kilometers from Earth. These X-rays are generated through a process known as charge exchange, which occurs when highly energetic particles in the solar wind collide with neutral atoms and molecules streaming off the comet's nucleus. Electrons are transferred, and the resulting excited ions emit X-rays as they return to lower energy states. This phenomenon was independently supported by observations from JAXA's JWST mission, which detected a faint but extended X-ray glow stretching nearly 400,000 kilometers from the nucleus. The sheer scale of this emission region highlights the intensity of the interaction between the comet's expanding atmosphere and the solar wind. More importantly, X-ray observations unlock a realm of information that is largely inaccessible to optical and ultraviolet telescopes. Light elements, such as hydrogen and nitrogen, which are fundamental to understanding volatile chemistry, are notoriously difficult to detect with conventional methods. X-rays provide a sensitive probe for these elements, allowing scientists to infer their abundance and distribution within the comet's coma. The implications of these measurements are far-reaching. By comparing the elemental ratios observed in 3I/Atlas with those found in comets formed within the solar system, researchers can directly assess whether the building blocks of planetary systems share a common chemical blueprint across the galaxy. Similar ratios would suggest that planet formation follows broadly universal rules, while significant differences could indicate that local stellar environments play a dominant role in shaping planetary chemistry. In this sense, the X-ray data do not merely describe the comet itself. They offer clues about the diversity of planetary systems beyond our own. As the comet continued on its outbound trajectory, observation campaigns intensified to capture as much data as possible before it faded from view. On December 19, 2025, 3I/Atlas made its closest approach to Earth, passing at a distance of approximately 270 million kilometers, or about 1.8 astronomical units. While this posed no danger to the planet, the geometry of the encounter provided an optimal window for detailed measurements. At the same time, spacecraft orbiting Mars, including the Mars Reconnaissance Orbiter and the MAVEN mission, played a critical role in tracking the comet when it was temporarily lost in the sun's glare from Earth-based perspectives. This multi-point tracking approach allowed scientists to maintain continuous coverage, ensuring that key phases of the comet's evolution were not missed. The compositional analysis of 3I/Atlas has already yielded remarkable results. Observations from the James Webb Space Telescope detected clear signatures of water ice, carbon dioxide, and carbon monoxide, all familiar components in solar system comets. However, the presence of carbonyl sulfide and an unexpected signature of nickel added an intriguing twist. Nickel, a metal more commonly associated with rocky asteroids, suggests either unusual formation conditions or complex processing within the comet's parent system. Its detection raises questions about how metals are incorporated into icy bodies and whether similar processes operate in other planetary disks. Taken together, these findings paint a picture of an object that is at once familiar and alien. In many respects, 3I/Atlas behaves like a typical comet, developing a coma and tail as solar heating drives sublimation. Yet its origin beyond the solar system, its evolving chemistry, and its unprecedented X-ray emissions set it apart as a messenger from another star. As it now departs, carrying with it the secrets of a distant planetary disk, scientists are left with an extraordinary dataset that will be analyzed for years to come. Although the encounter itself is brief on cosmic timescales, the insights gained from 3I/Atlas may permanently reshape our understanding of how planetary systems form, evolve, and distribute their material across the galaxy.